Greetings. In this video, we're going to discuss structural trusses. We will talk about the parts of a truss, the design, and structural considerations. We'll look a little bit at manufacturing and talk a bit about loading, of course. So, a truss is a single plane framework of individual structural members connected at their ends to form a series of triangles and are designed typically to span very long distances. So, single plane, so that is falls in this first category, actually, the single plane part of it typically. The planar truss is the one where all members and nodes lie in a two-dimensional plane, and that's what we see here. These are our most common trusses, what we think of typically when we hear trusses. A space truss has the members and the nodes extending into the third dimension, and that's what we see here on the right. So for vocabulary, we need to know the different parts of a truss. So the top chords in a truss are, or the top beams, it says here, are called the top chords and are generally in compression. So that's these members here. So kind of, there are some similarities between trusses and beams, which we will talk about. So the top is typically in compression here, top chords. Bottom chords, typically in tension, similar to a beam as well. The interior beams, I'm calling them beams here, it's kind of a different kind of name there, but webs, we call these webs right here, the interior diagonals. All right, and then the areas inside the webs are called panels, so that's the empty space called a panel. Webs are more specifically designed as diagonals or verticals, so these are diagonals. Sometimes they do stand vertically. Any truss member not necessary for stability is called a redundant member. So in a truss like this, I would expect all of them to be working here, all of these web pieces, but in some larger trusses, perhaps, depending on the configuration and the bearing and the load requirements, some of them might not actually be structurally doing any work. Also important here is the span. So the span is not the length of the truss, the span is the bearing, basically, where it is out of bearings there. So we can see right there that little white symbol there is the 2x4 or the top, or 2x6, whatever it is, the top of the wall right there. That is the bearing, and right there as well. So we have an overhang. The heel is directly above the bearing right there, and splices do occur. And what else? Overall height is the vertical height we see right there, and that's the length of it, or the most of it there. That's the most important parts of the truss. So originally they were hand built on site using nailed plywood gussets, and I actually worked on a really nice house where we built some homemade site-built trusses. They were nice, curved actually. They're kind of specialty items, very short span, so that's why we kind of built them up ourselves. But that's what we see here, some kind of homemade trusses, if you will, and I see it kind of a plate added here as well. They offered acceptable spans, but they took a lot of time to build. And then in the 1950s, the metal connector plate was invented, and then it transformed the whole industry and the prevalence of trusses, of course. So the popularity grew because they could be prefabricated using highly efficient production techniques, and then so they offer economy, inexpensive relative to stick building or frame building piece by piece or roof. They delivered quickly, and they were put into place very quickly as well. Let's see if this will actually play right here. That worked. And we could see them constructing the truss on a jig. So we see pieces here, metal pieces being kind of put in like this large pegboard, and they are holding the trusses where they belong, locking the pieces in, locating the gusset plates, which are razor sharp, and the hydraulic press comes to finish the process. So they are quite flimsy by themselves, but once they get put in place and locked in place with the plywood on top or the roof sheathing, it all becomes much more rigid. and then off to the job site. Okay, so that's what it looks like to construct the trusses. And now for the design of trusses. So truss design is completed by the manufacturer. This is important. So the structural engineer or the architect do not actually design the trusses. The building designer does provide very important pertinent information, and the manufacturer takes it from there. So this is all code information, and that's what the engineers are. The structural engineer will typically be responsible for. So the size of the building, what type of a building it is, the span and the shape of the trusses, where exactly the trusses are supported, what dead weight will be above the truss, the roof construction that is, the loads. So yes, the engineer determines the snow and roof loads, and then any important pertinent geometry, pitches, heel heights, overhangs, cantilever details. So they provide all of that, and then the truss manufacturer will complete the job and usually come up with the interior web design. So as long as there's no attic, it's really just left up to the manufacturer to determine that. Okay, so this doesn't happen too often in the design of buildings, but sometimes, yes, the design is handed over to the manufacturers, the people who are best suited to do the job. And we'll see something similar to that when we dig into steel and how involved that design process is too. And it's not all the structural engineer that does that as well. Okay, the statics of trusses. So the formulas, the math that settles and that determines that these things are stable, in fact. So a truss is comprised of members that are all connected by means of pin joints, and which is supported at both ends by a hinged joints or rollers. It is described as being statically determinate. So statically determined. So this is going back to the original truss formula when math was first applied to these trusses, and they were being scientifically proven that they will do the work that they're expected to do. And statically determinate means that yes, the math the math equations could be solved. That it's possible to mathematically determine that yes, this truss is stable and will carry the load. That's what statically determinate meant. The formula made some assumptions just for consistency, like all formulas typically will, and the joints are pinned, and that's what we see here. So and you'll see more about this in the video, the accompanying video from the great courses. And so it was kind of an interesting case where the mathematicians or the engineers that came up with the formulas, they made the assumption on the pin joints, and then which is kind of a theoretical assumption. It didn't truly mean that they needed to be pinned, but for math purposes, they needed something to fill in there. Some assumption had to be made. But then, interestingly, the builders followed suit with the formula, and they started pinning them all. And joints and rollers, we talked a lot about that, the connection or the bearing points. So that's the roller there. But in a lot of so this is the beautiful East Falls Bridge near our Philadelphia University. And we will see, and you will hopefully now spot, if you haven't paid attention, that you'll see that a lot of these beautiful old truss bridges around Philadelphia or wherever you are with your travels will find actual big, large, oversized pins like that one. Okay, so every member in a truss is in pure compression or pure tension, right? Shear and bending and more complex stresses are all practically at zero. And this makes the trusses easy to analyze, easier. It also makes the truss physically stronger than other ways of arranging material because nearly every material can hold a much larger load in tension or compression than in shear, bending, torsion, or other kind. So compression and tension are easier for most materials to deal with. Therefore, it makes these trusses very efficient. Okay, so all these interior pieces are either, and that's what we see, these arrows. So this one would be in compression, being pushed on. This web would be in tension, being pulled on. The top chords are in compression, 2 arrows facing each other. The bottom chord is in tension, 2 arrows opposing each other, facing in opposite directions. And then you see a little dashed line there, kind of shows a bending. kind of similar to the beam. And this is, of course, showing that we have a uniform load being applied to the top, snow, for example. Okay. And also just important to note here that about materials working better in tension and compression, wood and steel in particular handle the forces of tension and compression equally well. So we've mentioned probably briefly, but we will be digging into it much deeper when we talk in more depth about concrete, for example, that concrete is great in compression but very, very poor in tension. That's why you typically aren't going to see concrete trusses. It doesn't really make a lot of sense. But steel and wood handle both of these equally well. So they're ideal materials for trusses. All right, planar trusses we discussed. Everything's in a two-dimensional plane. Like we see there, bicycle frames. So yes, there are trusses all around us. They're also very common in building airplanes. Of course, those would be three-dimensional trusses. This slide talks about the efficiency of the and the power of the truss down here at the bottom. Composite trusses leading the pack in terms of span. So this is meters. So I don't know the exact conversion, but this is probably a good 60 plus feet, I believe. So trusses outwork everybody else in that regard. So these are some other structural compositions or opportunities, possibilities, and they range from the reinforced flat concrete slab that could span, relatively small amounts, and then moving up to fabricated beams with web openings being up near the top, or composite beams again up near the top of trusses. Considering their lightweight and just how far they could work because of their being triangulated, are the leaders of the pack. Very efficient structural form. And so when talking about efficiency, the weight also is an important part of the conversation. So solid girders or beams of equal strength would weigh so much more compared to the truss. And that's part of the reason why here they could actually take away some material. It's not needed there. That part of the web is not doing any work. So we could reduce and take away material. And I've shared with you some of the popsicle bridges that we've built. So this is an older one now, but this very, very light bridge weighing in at 6.9 ounces or 0.43 of a pound, so less than a half of a pound, carries 175 pounds, ends up with a structural rating of 406. So even in our small, fun classroom experiments, we could see the enormous power of the truss. Okay, and here we could see a truss being loaded. Let's see, that's going to play great. All right, so 2 combined flat trusses. Whoops. Sorry about that. I don't think we need the sound effects. So we're going to see this truss doing a lot of work. So double flat truss, nearly 12 inches high, nearly 20 feet long, very tall, very long. And deflections begin at about 110 pounds. So how much weight is this thing going to carry? An impressive amount of weight. I'm not sure that it's the safest way to load a truss. I think ideally a hydraulic press with no one standing so close would be safer. There we go. And then there's fracture. Impressive. An impressive amount of weight, and it just buckled under the weight. All right, great visual there. Okay, truss types. So 2 basic types of trusses. Pitch trusses or common trusses, characterized by their triangular shape. That's most of what we see here, are triangulated ones or triangular shaped ones, most often used in roof construction. Some common trusses are typically named by their web configuration. That's how they are named. The cord size and the web configuration are determined by span, loading, and spacing. That's very important. All right, again, I often kid, but usually whenever the question comes up, how is something determined? The answer is typically building codes, span, load, and spacing. Those are the determining factors. And the other type is the parallel cord truss that we see right here. So top and bottom cords are running parallel to each other. So yes, we could see some roof trusses that also have parallel cords being incorporated into hip. So the hips trusses become a little more complicated. They take a couple specialty pieces in order to create this kind of pyramidal configuration. Okay, and then here, yes, for a vaulted ceiling in a room, perhaps a master bedroom or some sort of second floor great room, you might have a vaulted ceiling, and you get a truss to accommodate that. Okay, this is a very important comparison between beams and trusses. All right, so wide flange steel beams, most common efficient type of framing for short to medium spans. Most of their material is concentrated in the flanges at the greatest distance from the neutral axis. All right, we've talked about the neutral axis some, and it's saying that the neutral axis is down here in the middle, and they push as much material as possible away from it for greater stability, and it ends up down in the flanges. Okay. So this is, yes, from our other video from the great courses, and you will watch that. So it discusses the important concept of the area of moment of inertia. Okay, the I in the equation. So it's a measure of the member's cross section's ability to resist bending. The moment of inertia depends not only on the mass, but also the location of the mass relative to a point of rotation. The further the mass from the rotating point, the greater the moment of inertia. So by spreading out, they become more stable rather than being tight and compact. Okay. However, for the I-beams, as the spans and the loads increase, the dead load of the beam, the weight of the beam itself, increases disproportionately, making the beam much less efficient. All right. The truss separates those flanges a greater distance and connects them with these thin, slender web members. So it's in effect a built-up beam with a discontinuous web. All right, conceptually, that's very important. The truss could be thought of as a built-up beam with a discontinuous web. All right, so steel beams could be built up of several different pieces. Smaller ones are typically hot rolled right from the mill as is, but larger girders are built up with several different pieces, often stiffeners and plates within. So steel beams can be built up, and we will see that when we dig deeper into steel. So conceptually, we could just think of a truss as a built up steel beam, and we've pushed those top and bottom cords as far apart as possible for greater stability, and have a discontinuous and very lightweight web. All right, very lightweight web. The amount of material in here is very, very little when compared to an I-beam, and that's what makes gives them their great efficiency. So the truss cords, top and bottom cords, are like the flanges of the steel beam, and the web members of the truss are similar to the webs of the beam. Okay, similar. For simple span truss, just like an I-beam, the top chord's in compression, the bottom is in tension. Yes. In the beam here, shear is resisted by the stresses in the web, right? That's resisting shear right there, the webs. In a truss, shear is resisted by the tensile and compressive forces in the web members, depending on their direction. So similar, all right? But again, doing it much more efficiently. These are resisting any shear. And back to the bridge. So we saw this slide already, so I do not have to repeat this. Well, this is talking about, again, those truss members being in either pure compression or pure tension. So here's a nice depiction of that. So there we see our pins, and so this is, one of the two options. So they're either in compression or they're in tension. Secondary stresses, shear and bending forces could typically be ignored because they're so negligible. Okay. Nowadays, pins and hinges are rarely used. It's much more economical to connect them by welding or bolting. All right, these are old gussets. This restrains the rotation and induces small bending or shear stresses actually into the members, in addition to the primary axial stresses of tension and compression. All right, so the primary forces again are the tension and compression. But however, now that we are no longer using these bolts or pins, and now we are really securing them by welding or bolting, now they are actually starting to bend a little bit, and they are. So some shear stresses and bending stresses are actually being induced because of the new manner in which they are being joined. All right. After the forces in the truss members have been determined, the truss members can be designed. Okay, so yes, we have to determine the forces, and then the members are designed. And this kind of goes back to what we were talking about with the columns, and just in general, all structural members, how it's a very repetitive process. So we have to figure out the forces, and then the members are designed. And then after the members are designed, sometimes that dead weight affects the design as well. So then again, more repetition. So it's kind of this continuous cycle of design considerations. Compression members are designed as columns. Tension members, so in general, just basically anything that experiences compression is kind of treated as a column. Tension members must have a sufficient cross section in that area to so that the allowable tensile stresses are not exceeded. So we talked about this as well, talking about the importance of tension and how it is measured in cross section, the stresses in the cross section. All right, so those tensile ones, the webs that are experiencing tension must be wide enough, thick enough in cross section. All right, so tensile forces and cross section go together, hand in hand. All right. Although length is an important factor in the design of compressive members because of buckling, it's less important for tensile members. All right. Recall Leonardo's incorrect conclusions regarding the length of wires and the importance of the brace length of columns. Okay. So we talked about all this before. So the shorter the column, the less likely it is to suffer from buckling. Right, and that's why we'd add these braces in. We'd reduce the size of this. If this is a 20-foot column, now the effective length is 10, and it will resist buckling much better. So that is why the length of a member in compression is very important, just like the length of a column is very important. However, a rope does not care if it's 10 feet or 100 feet or 1,000 feet. It doesn't make a difference to the rope. As long as this weight remains the same, the length of the rope does not matter. The thickness or the cross section of the rope does matter. Okay, so tensile members can be very long, but they need to have the adequate cross section. All right, and a span chart. So the optimum depth of a span ratio of a truss is about 1 to 10. All right, so a truss that's 100 feet long should be 10 feet deep. All right, so that's, again, just some rules of thumb to help get us started before we get into that repetitive process of actual calculations. All right, so here we see some truss depths, and then here we have this spacing, and then we connect the dots, and we could see that 16. Let's just look down here at the bottom. A truss that's 2 feet deep, and if they're 12 inches on center, which is very close, we could get nearly a 38-foot span. At 16 inches on center, it drops to nearly 33 feet. At about 20 inches on center, it's down to about 30 inches, but still some pretty significant spans for a truss that's only 2 feet deep. That's not particularly deep. That's similar to the video that we just saw. All right. And the remainder of this presentation is really just a look at some examples of trusses that are we see in everyday usage. And an important point about trusses that they are very labor intensive to make. So often we don't see them in particularly interesting applications. They're very common when they are and very suitable for being mass produced. So electricity pylons, of course we see them in bridges, beautiful. This one's pretty simple, pretty straightforward truss. Of course we see them in roofs, so yes, in some assembly type or gathering spaces like malls, they often will have roofs that are visible, and these trusses are quite attractive and nice, kind of lightweight in appearance. So that's, again, of course, a space truss in 3 dimensions. A support underneath a bridge, and here we see trusses within trusses. So trusses. So this whole structure is a truss, and it is comprised of smaller trusses. So this is these are kind of like they appear to me to be kind of 2 planar trusses on both sides, joined by trusses. So I would imagine this whole piece would be designed as a truss, as is this, and then joined by other trusses. And here the Hong Kong Bank of China. And when we dig into skyscrapers, the great skyscraper race and the development of high rises, we'll see a kind of a breakthrough point when engineers stopped looking at high rises as this kind of building these towers of just steel, simple steel columns. Kind of like the Empire State Building was just a kind of a forest of columns, which really impedes the architectural qualities inside the building with having to have so many interior columns. So they stopped thinking about it like that, and they started thinking about a high rise, like what if we thought of it as one big structural member itself, and they started thinking about it as a truss standing on end. And that allowed for just huge developments in the development of high rises. There no longer, again, that forest of columns that was necessary. So this is essentially kind of a flagpole of a truss just standing on edge. The beautiful Institute of Contemporary Art in Boston with this awesome cantilever. So this entire, so the lines are a little faint there, but this entire space is one big truss, and that's what we see there. So it's kind of a 2-story truss, at least 2 stories. I just love this image here. That's that space there. So some sort of a computer sitting lab where you could look down and see the river. And now some more mundane, pictures of what goes wrong with kind of carelessness in the manufacturing process. Gusset plates that are not placed properly, so going up looking in attics. So tensile forces have pulled this one apart. These are the razor sharp gusset plates, but some significant forces, some loading or something happened here where this actually pulled away from it. Same here. So quality control could be an issue. Gusset plates. Pre-gusset plates. So a home, I call them homemade, but a site-built truss, and large connectors in principle could be a good thing, but when you take out that much material from the beam, it becomes a weak point. And so not surprisingly, it appears like some sort of a tension has pulled all of this apart. And not surprisingly, all of the damage occurred at these connections where they removed a significant amount of material from the beam. The installation of trusses is a very important matter, and a lot of safety concerns with that. So this photograph was taken 10 seconds before these 52-foot scissor trusses collapsed. No wind. So the top cord is buckling. So we see some intense buckling from a lack of proper bracing. All right, so not braced properly. So there are a lot of safety concerns and proper procedures that need to be followed on the job site when this occurs. Obviously, hopefully this gave everybody enough time to get away from this. This looks like a bad situation happening. And again here, a show, a truss stage that was taken down. So these trusses are very common in the entertainment industry. Again, lightweight for travel, easy to erect, but obviously care was not taken. Proper care was not taken here, and there was a potentially very damaging accident occurred here. Hopefully nobody was hurt. And because trusses do have the most potential for the greatest reaches than all other beam types and other structural combinations, they are often, unfortunately, involved in great accidents, because this is where engineers push their abilities because of their, inherent abilities, but sometimes obviously pushed too far or something was overlooked. And we will later in the course look at building failures. So again, potentially, potentially devastating. And arenas have experienced their fair share of significant structural failures. Very scary. And of course, trusses in space. Very sharp looking image. Okay, thank you. I hope you enjoyed that.